Hi guys, so I'm going to be showing you how to do all of these problems right here. We do have the answers, which is good, so we know if we got the problem right. So let's get started. So the first problem says a wheel rotating about a fixed axis has a angular position given by theta equals 3 minus 2t cubed, where theta is measured in radians and t in seconds. What is the angular acceleration of the wheel at t equals 2 seconds? So right off the bat, we notice a few things that are very helpful and make the problem a lot easier. And that would be a wheel, and it is rotating. So we have this sort of movement, right? And we have a fixed axis, and we want to find angular acceleration, and we're given angular position. So I made a formula sheet, and as you know, acceleration, just in general, acceleration is the double derivative. Is that even what you call it? I don't know. It's the double derivative, I guess, of the position. Our angular position is 3 minus 2t cubed. And we want to find it at t equals 2 seconds. Double derivative. What is it called? I swear it's called double derivative. So d in respect to time, because t is our variable here. And then so the first derivative of this would be, since this is a variable, because I haven't taken calculus in a while, so I'm just gonna explain it how I view it. So 3, since it's a constant, not a variable. Since 3 is a constant, it would be 0. And then we have minus 2. Let's bring that down. And this would be 3. Since we're doing derivative, we're taking down this 3. And then t. And then this 3 is minus by 1. So it'd be 2. So our first derivative would be minus 6t squared, right? Now we're finding the second derivative of this number, which would be minus 6 times that variable, or that number, t1. And this would be negative 12t. So this is our angular acceleration, because we found the double derivative of the position. So this is now our formula for acceleration. And now we can plug in this too. So negative 12 times 2 equals negative 24. And this would be measured in radians per second squared, because we're finding that angular acceleration, and that is what the units are for angular acceleration, is radians per second squared. And that's what we have for the answer. So we got it right. And number 2 says, a wheel rotating about a fixed axis with a constant angular acceleration of 2 rads turn into 2.4 revolutions during a 2-second time interval. What is the angular velocity at the end of this time interval? Okay, so I'm going to be writing our knowns. And sorry if my camera keeps unfocusing and focusing, and I don't know why it's doing this. But anyways, so number 2, we know our angular acceleration, which is equal to 2 rads. I say rads. I don't know why. I just look at this really quickly and I'm like, rads, but we all know it's radians per second squared. Okay. Anyways, we know that there's a 2-point revolutions, which means that this object is circling around the axis 2.4 times. That's all it means. And we know our time equals 2 seconds, and we want to find angular velocity, which is this omega sign. This is W. I always say W, but I mean omega. So the formula to find our final W is going to be W final equals W initial plus AT. Now, we do not know W final, and we don't know W initial, and we know these two, which is angular velocity times t. To find this initial W, we can use this formula where theta equals theta initial plus W initial t plus 1/2 AT squared. Now, this formula is only the case for fixed axis rotation with constant acceleration, which I have written right here. I also have it in my formula sheet, as you can see right here. This is the two formulas we're using. This is how to find W final, this is how to find W initial, and we need to plug this into here. We know that there is no initial angle because we are only given 2.4 revolutions. And this angle will only take radians. So how we can convert this 2.4 revolution into radians is this simple conversion. There are 2 pi radians in every 1 revolution, meaning a circle is 2 pi. So there's going to be 2.4 circles, right? So there's going to be, we're going to multiply that by 2 pi. I'm just going to leave this at 2.4 times 2 pi. I'm not going to actually do the math until the very end. So we can plug this into our theta here. So 2.4 times 2 pi equals, and we don't know our W initial, or that's what we're trying to find. Our T is 2, our time, plus 1/2, and our angular acceleration is going to be 2 times time 2 squared. Now this 1/2 2 is going to cancel, so we can already cross that out. And if you do all the math, you should come out with W initial equals 5.54 radians per second. Now, we have our initial, and now we can plug this into our final equation. So W final equals 5.54 rads per second plus this 2 from the angular acceleration times our time, which is also 2. And this should equal, because this is 4 plus 5 is 9. So your answer is 9.54. And this is going to be rads per second. And that is what we got. That's the actual answer right here. So that means we got it right. Okay, so we're going to be doing the third problem now, which is a wheel rotating about a fixed axis with a constant angular acceleration of 2 rads, starts from rest at t equals 0. The wheel has a diameter of 20 centimeters. What is the magnitude of the total linear acceleration of a point on the outer edge of the wheel at t equals 0.6 seconds? Now let's go ahead and write our knowns. We know that we have an angular acceleration of 2 rads. We know it starts at t equals 0, or starts from rest. We know that the diameter equals 20 centimeters. And we never really use centimeters when it comes to SI units. We usually use meters, so we're going to convert that. So 20 centimeters equals to 0.2 meters, because you're moving the decimal over to the left twice. And now we don't really ever use diameter in any of our formulas, so we mostly use radius. So we're going to find the radius of this, so half of 0.2 is 0.1. So it's 0.1 meters. Okay, sorry, I messed up right there. We want to find the total linear acceleration. So we want to find a total. And we know that our t equals 0.6 seconds. So the formula for total linear acceleration, according to my formula sheet, is going to be a total equals the square root of these two accelerations. And that's going to be a tangential acceleration and radial acceleration, only if the particle is moving in a circle, right? So we are trying to achieve this formula, but we need AT, AR. So we can find AR using this formula, or AT, I mean, tangential acceleration. So let's find that first. We have A tan equals R alpha. And our R is 0.1, alpha is 2, which should be 0.2, and it's going to be meters per second because we're doing linear acceleration. Now we can find our A rad, W squared R. And since we don't have our W, we're going to have to find that as well. So the formula we can use is going to be W equals W initial plus alpha t. And we know that since this object starts from rest, we're not going to have a W initial, which is the velocity, right? So we know our alpha, which is 2, and we know our time, which is 0.6. And doing this, calculating this, will result in 1.2 rads per second. So this is our W, and we can now plug this into our ARAD equation, which is going to be 1.2 squared, and R is going to be 0.1. And this should equal to 0.144 meters per second squared. Once again, meters per second squared because linear acceleration. Now we can now plug in this to our total equation, which was the square root of AT squared plus AR squared. Almost like Pythagorean theorem. And now plugging this in, AT is going to be 0.2 squared plus AR, which is going to be 0.144 squared. And then this will equal 0.25 meters per second squared. And that is your total linear acceleration. And the answer was 0.25, so we are correct. So we can work on our next problem. A wheel rotates about a fixed axis with a constant angular acceleration of 4 rads. The diameter of the wheel is 40 centimeters. What is the linear speed of a point on the rim of the wheel at an instant when that point has a total linear acceleration with a magnitude of 1.2? Okay. Now let's go ahead and just write our knowns so that we don't feel very overwhelmed. I'm not the best at word problems, so I find that writing everything you know and looking at them and just seeing the general overview really helps solve these problems and understand what you need to find. So we have a fixed axis with a constant angular acceleration once again. So this is going to be our alpha, which is 4 rads. We know the diameter equals 40 centimeters. Once again, just like the last problem, we're not going to need diameters. We're going to need radius, and it's going to be in centimeters. So the radius is going to be 0.2 meters. We have the total linear acceleration, which actually helps a lot, which is A total equals 1.2 meters per second squared. We need to use this equation, but we already have A total, so we can use these to our advantage to find what they want us to find, which is going to be linear speed. So they want to know velocity, pretty much. We can find velocity because we want to know AT, AR. AR has velocity in the equation. It could be this one or this formula. They have V in the formula, so we can use this to our advantage. But we still need to find A tan and A rad. So let's do AR first, which is V squared over R. So we're going to leave it at this. We're going to leave it our formula like this because we don't know what V squared is. And now we're going to find AT, which is equal to r alpha. And that is equal to 0.2 times 4. And that is going to be 0.8. Okay. So now we have AT, AR, and we can plug into this equation. So AT or A total equals the square root of AT squared plus AR squared. And this is equal to, and we have AT, which is 1.2, so we can go ahead and plug that in. Or this means total, and this means tan, so we can't get those confused. This is also total. So A tan is going to be 0.8 squared plus V squared over 0.2, and all of this squared. This is going to be 1.2 still equals 2, and then square root of 0.8 squared is going to be 0.64 plus V to the fourth over 0.04, and square root of all of that. And now we can get rid of this square root by squaring the whole problem. This is going to get 1.44 equals, and then this is going to be 0.64 plus V4 over 0.04. And now we can start isolating our velocity that we are trying to find right here. So we can minus 0.64 from this problem, and then you can multiply you can multiply that, whatever number you get, with 0.04, and then which is going to be equal to 0.032. And you want to find the, not square root, but the fourth to the, what is this, fourth to the square root? I think, yeah, of V4 to get rid of that fourth exponent. And you're going to do the same to the side. So V equals 0.42 meters per second, but it could also be 42 centimeters per second as well. And that is correct because it says right here 42 centimeters per second. Now we can do the last problem. A rod of length 1 meter has a mass per unit length given by lambda equals 2 plus 1 x squared, where lambda is in kilograms per meters. The rod is placed on the x-axis going from x equals 0 meters to x equals 1 meter. What is the moment of inertia of the rod in kilograms times meters squared about the y-axis? Okay, writing our knowns once again. Sorry, I messed up again. But it's going to be a rod this time. That's the difference between this equation and the other four. So we know that the length of the rod is going to be equals 1 meter. We know that the mass, or lambda, is equal to 2 plus x squared, and this is going to be measured in kilograms times or over meters. And we know we're going from x equals 0 meters to x equals 1 meters. And we know our axis is going to be on the y-axis, and we want to find our moment of inertia. So we can look at the formula of inertia, or the moment of inertia for a continuous body mass distribution, which is going to be equal to the integral of the radius squared in respect to mass. So this is our formula. I equals r squared dm, where m is going to be the mass, and we're going to go from 0 to 1 because our x was 0 and now our second x is 1. We're going to start substituting into our integral. So we can do dm equals lambda dx, or not dx, dr in this case actually. So we can now plug this into our equation, which is equal to 0, 1, r2, and it's going to be x, or not x, it's lambda. I don't know why. I keep looking at this and I'm thinking it's an x. So lambda dr. And now we can plug in our lambda, which we know is 2 plus x squared. We can plug this into our equation now, which is equal to 0 to 1 r squared 2 plus, and in this case we can actually use, they said it was x, but I'm going to use r. So if you see how this is an x, I'm going to use r because this is r and we're doing in respect to r. So plus r squared dr. Now we can distribute this r squared. We have 2r squared plus r to the 4th dr. And now we need to integrate this. And how you do that is you add this 2 by 1, or this exponent by 1, and then you divide the whole variable by that number. So it's going to be 2r cubed divided by cube plus r5 over 5. And this is going from the bounds 0 to 1. So we're still trying to find I. So I equals, and now 1, plugging it into the r's, is going to be 2 over 3 plus 1/5. And this is 0, so that will make these 0. So it's just 1 minus 0. And now we have this problem, and now we can make the denominator equal, which is going to be 15. So 10 over 15 plus 3 over 15. And this is equal to 13 over 15. And if you put that in your calculator, it should give you 0.867. And our units are going to be kilograms times meters squared. And that is the answer to number 5, as you can see here.